So the last section in chapter 10 is about geometric probability. So by the end of this lesson, you should be able to calculate geometric probabilities and then use them to predict results in real life. So think back to when you learned probability. It's the set of all possible outcomes of an experiment, which is the sample space, divided by any outcomes, which is called the event. So if every outcome in the sample space is equally likely, the theoretical probability is number of outcomes in the event divided by the number of outcomes in the sample space. And for everything that we're doing now, we're assuming that every outcome is equally likely. So it's not like a bullseye where you're trying to get into the center. You're just shooting your arrow and every single space is just as likely for you to hit. So geometric probability is used when an experiment has an infinite number of outcomes. In geometric probability, the probability of an event is based on the ratio of the geometric measures, such as length or area. So that's what we're going to do today, is equate this probability with length, angle measures, and area. And here's some examples. So let's say we're talking about length. You have this segment right here. The total length is AD, and then I just want all the points on BC. So when I do this, I'm going to set up the probability of just landing on here, however long that is, divided by landing on the entire line. Angle measure is pretty easy because it's always divided by 360 because you're going to have a circle that you're finding the angle measures of. Your event is all the points in the shaded region, and they'll tell you this is like 60 degrees. So then all you have to do is divide by 360. Area, the event could be just in this shaded part, but the sample space is anywhere in this rectangle. So you're going to take those two areas and divide them. So let's start with length. It says a point is chosen randomly on PS. Find the probability of each event. So remember, there's infinite possibilities. There's infinite points on this line. If we want the point to land on RS, we need to divide the length of RS by the length of PS, the whole line. So from R to S is just 5, and P to S is 7 plus 13, which is 20, plus the 5 more, which is 25. And we like to express probability as a percent. So if you divide 5 by 25, you end up with a 20% chance of landing on RS. Now, this next one's a little different because we want to know the probability that something is not on QR. So for this, we're going to take the length of PS and subtract the length of QR because we don't want it on there, and then divide by PS. You could also do this as the probability of landing on PQ and RS divided by PS because those are your only other options. But either way, we don't want this 13 here. So the length of the whole thing's 25 minus the 13 that we don't want divided by 25. So you end up dividing 12 and 25. And if you throw that in your calculator, you end up with a 48% chance of not landing on QR. So that was length. Angle measures, remember, have a circle, and we're always going to divide by 360 because that's the total distance around. So if I want to find the probability of landing on yellow, there's 140 degrees that are yellow divided by 360 degrees total. And if you divide those two things out, you end up with about 0.39. So about 39% of the time you're going to land on yellow. Now when we have one like this where it asks us landing on blue or red, we are perfectly happy with it landing on red or on blue. So you just get to add them up and then always divide by 360. So 60 plus 52 will give us the numerator, and we want to divide that by the total number of degrees that we have. So 112 divided by 360 gives us about 31% of the time we're going to land on blue or red. So that was length and angle measures, and now our last one is area. So find the probability that a point chosen randomly inside the rectangle is in each shape, round to the nearest hundredth. So my rectangle is the sample space. So for both of these, the denominator is going to be the rectangle. For the first one, I want to know landing in the circle. So we got to find the area of the circle and divide by the area of the rectangle. Now the rectangle is super easy because we're just going to do base times height, which is 28, times 50. And if you multiply those together, you get 1400. Now the circle, remember the area is pi r squared. And my radius is not 18. My radius is only 9. So pi times 9 squared, or 81 pi. Because remember, radius is just half of that. So if you do 81 times pi and divide that by 1400, you get about 18% of the time, if you throw a dart totally at random, that you would end up inside the circle. Now the next one we got to figure out is the trapezoid. And with the trapezoid, we have to remember the formula for a trapezoid. And remember, you're going to take the two bases, cut them in half once you add them together, and multiply by the height. So my two bases are 34 and 16. And then we'll multiply that by the height, which is that 18, because that is the height of the circle as well. Cut that in half. And then remember we got to divide by the rectangle, which we know is 1400. So 34 plus 16 gives us 50. You cut that in half, you get 25. And then we got to multiply by 18. So the trapezoid is 450 divided by the 1400, that's the rectangle. And about 32% of the time, we're going to end up inside that trapezoid. Always make sure your answers make sense when you're dealing with probability. That trapezoid is big, but if you got something like 72% of the time, it's not taking up like 3/4 of the rectangle. So double check that your answer makes sense. So those are the three types of problems that you're going to see: length, angle measures, and area. So you should be able to calculate them and then predict those results in real life, and we'll talk more about that in class. Write down any questions you have and we can go over them then. Enjoy your night.